Let us move on to example 2.10. So a hydroelectric power station has a reservoir of area 2.4 square kilometers and the capacity is 5 into 10 power 6 meter cubes. So the effective head of water is 100 meters. The penstock turbine and generation efficiencies are also given to you. This is just you can simply find out the overall efficiency by multiplying all of these efficiencies. You have to calculate the total electrical energy that can be generated from the power station. So number one is this, and number two, you have to find out that if a load of 15,000 kilowatt has been supplied for 3 hours, how much water will fall in the reservoir which you have created. So let us look at this example. It looks to be very interesting, and let us look at this example. So how much weight of the water is available to you, that you can find out by multiplying the volume of the reservoir, which is 5 into 10 power 6 meter cube, with the weight of 1 meter cube of water. So for 1 meter cube of water you have a weight of 1000 kilograms. That is given by the density of water. So if you multiply these two, you get the volume of the reservoir and multiplied by weight of the 1 meter cube of water. That gives you the total weight of the water, or in this case we should say that you get the mass of the water, and if you want to find out the weight of the water, you multiply this mass, which comes out to be 500 times power 9 by 9.8, which is the gravitational acceleration, and you get the weight in newtons. So the overall efficiency can also be calculated by multiplying the efficiencies which are given in the problem. So 0.726 is the overall efficiency. So how much electrical energy that can be generated? So the weight of the water into the height into the overall efficiency is the electrical energy that can be generated. So 5 into 10 power 9 into 9.8, that is the weight of the water. Height is 100, and total efficiency is 0.726, and the energy which you get will be in joules or watt seconds. So you have to convert this energy into kilowatt hours. You have to divide by 1000 and 3600. So you get from this all of this derivation, you get the electrical energy that can be generated as 989,175 kilowatt hours. So now you have to find out how much will be the fall in the water level if 15,000 kilowatt load is supplied for 3 hours. So this is one of the ways in which you can do, and then we are going to look at an alternative way which you can use, and that is much simpler. But let us look at the problem at first via algebra. So if you specify that the fall in reservoir in 3 hours is x, then first of all you have to know what is the average discharge per second. So area of the reservoir into the fall in water level will give you the volume of the water which has left, and in how much time in 3 hours. So you have to convert those hours into seconds. So 3 into 3600 will give you the total number of seconds in that time, and if you simplify this, you get 222.2 x meter cube discharge per second. So this is not just meter cube volume of the water, this is the volume of the water which has been discharged in 1 second. So weight of the water available per second can be found from this volume volume which is discharged every second into the density of water into the gravitational acceleration. So that comes out to be 21.8 x into 10 power 5 newtons. So average power produced will be this weight multiplied by height into total overall efficiency. That you can also find out. The height is 100, and then overall efficiency is 0.726. So you get 15.84 x into 10 power 7 watts, or 15.84 x into 10 power 4 kilowatts. Now this is the average power produced if that much amount of water is released from this dam. You are given that the kilowatt hours which are produced are 15,000 kilowatts. So 15,000 kilowatts, from this you can see that 15,000 kilowatt power has been used for 3 hours. So 15,000 kilowatt of power has been used, and the derivation you have done tells you that 15.84 x into 10 power 4 kilowatt have been used. So you can easily equate these two, and you can get the x, which comes out to be 0.0947 meters or 9.47 centimeters. So the level of reservoir will fall by 9.47 centimeters in 3 hours if this much load is connected for 3 hours. Now let us look at the alternative method, which is much simpler as well. So the level of reservoir can be found by dividing the volume of the reservoir with the area of the reservoir. So volume of the reservoir is given to you 5 × 10⁻⁶. Area of reservoir is also given to you, which is 2.4 kilometers squared, and you get the meter squared version like this. And then you simply find out the level of the reservoir, the total level of the reservoir, which is 2.083 meters. So the level of the reservoir is 2.083 meters initially. The kilowatt hours generated in 3 hours are given by 15,000 kilowatts into 3, which gives you 45,000 kilowatt hours. Now, if 989,175 kilowatt hours were produced, which is the maximum energy which can be produced from this dam, the fall in reservoir level would be 2.083 meters. So the water level will fall by 2.083 meters. But if 45,000 kilowatt hours energy is produced, which is 15,000 kilowatt load running for 3 hours, the fall in the reservoir can be given by dividing this 2.083 with 989,175 and multiplying it with 45,000. So this is given here. This comes out to be 0.0947 meters or 9.47 centimeters. This method is much more easier, but I am going to give you an advice that you should follow the previous method, because that solidifies your concepts of algebra and solving problems through application of algebra. So that is extremely important quality in you, and if you are looking to get employed later on, you will get problems which you can only solve by specifying them in algebra, and you should use the previous method so that you have more practice of that method. This method can also be used, but this is only related to this particular topic. But the previous method which has been used to find out the same fall, that is a general method which is used in which is applicable in almost every situation. So I recommend that you use and perfect the knowledge of that method. Now let us look at example 2.11, and which is related to a run-of-river hydroelectric power plant. First of all, let me tell you what run-of-river hydroelectric power plant really is. This run-of-river hydroelectric power plant is one of the types of hydroelectric power plant, the other type being storage hydroelectric power plant, which we have normally discussed in our lectures, that a dam is created and water is stored in that dam, and then that water is let go and power is developed. But run-of-river plant, in run-of-river plant, there are no dams. There are only in some cases small reservoirs which are there to compensate for any momentary fluctuations in water flow rate. They are not there to store water. So run-of-river power plant, you have a river and you create a plant in the path of that river. You will allow all of the water from the river to pass through the turbines and generate electricity. So this is a run-of-the-river plant. So let us look at the problem. A factory is located near a waterfall where the usable head for power generation is 25 meters. The factory requires continuous power of 400 kilowatts throughout the year. So throughout the year, the factory must consume 400 kilowatts for all the time. The river flow in the year is 10 meter cube per second for 4 months, 6 meter cube per second for 2 months, and 1.5 meter cubes per second for 6 months. If the site is developed as a run-of-river type plant, if there is the run-of-river type plant is created on this site without storage, determine the standby capacity to be provided. So you have to determine how much capacity must be provided to serve the factory load if the power generated from the hydroelectric power station falls short. Assume that the overall efficiency of the plant is 80%. So let us look at this part first, and then we'll move on to this part, and we'll introduce this part, and then we'll move on to this part. So in this type of plant, the whole of the water stream is allowed to pass through the turbine for power generation. This is the run-of-river plant. Plant utilizes the water as and when available. So how much water is available will produce the electric power. Consequently, more power can be generated in a rainy season than in a dry season. Obviously, you do not have storage, so in a dry season you will be able to produce less power, and in a rainy season you will be able to produce more power. So it is given in your problem that the discharge available for 4 months is 10 meter cube per second. So for 4 months you will have this discharge available. So weight of the water available when this discharge is available is 10 into 1000 kilograms per second, kilograms per meter cube. That gives you 10 is power 4 into this gravitational acceleration is multiplied to get the weight in newtons. So 10 power 4 into 9.8 newtons. So the power developed in this way is the weight available every second into the head into the overall efficiency. That gives you 1962 into 10 power 3 watts or 1962 kilowatts. So 1962 kilowatts are available when discharge is 10 meter cube per second. So you can say that you can safely provide the load of 400 kilowatts if this much power is available to you. So this plant is more than capable of supplying this power during this time when the flow was 10 meter cube per second. Now let's repeat the same process for 6 meter cube per second. We get the power developed for 6 meter cube per second as 1962, which was the power available for 10 meter cube per second, into 6 divided by 10. You have to divide it by 10 because when the flow rate is 10 meter cube per second, you get the power of 1962 kilowatts. When the flow rate is 1 meter cube per second, you will get the power of 1962 divided by 10. And when it is 6 meter cube per second, you will get the power of 1962 into 6 divided by 10. That gives you 1177.2 kilowatts. This amount of power is still sufficient to provide the load of 400 kilowatts throughout that time for which this discharge is available. Now for the remainder 6 months, 1.5 meter cube per second discharge is available. For this much discharge, you will get the power of 294 kilowatts. Now this 294 kilowatts is not sufficient to provide this 400 kilowatt loads. So the deficiency of power will be 400 minus 294, or during this time 106 kilowatts of powers are short. So you have to provide these 106 kilowatts of power from a standby plant, from a standby unit, or from other generation sources during this period. So this is what happens if you don't create any sort of reservoir or storage, and you just use a run-of-the-river plant without any storage, without any small reservoir. So if we use reservoir, if a reservoir is arranged upstream, will any standby unit be necessary? What will be the excess power available? So this is the problem now, that now due to this 106 kilowatt which has to be provided from other means, you are creating a reservoir. So now if the reservoir is created, you have to tell if any standby unit will be still necessary. So let us move to find out this thing. So with reservoir, when reservoir is arranged upstream, we can store water. This permits regulated supply of water to turbines so that power output is constant throughout the year. So what happens now is that the amount of discharge available throughout the year is now the average discharge is now available throughout the year. In the year when a lot of water discharge was available, say 10 meter cube per second was available, some of that water was stored in the pond. The water stored in that pond was then used to ensure that in the other portions of the year the water was not below the minimum required level. So now an average discharge will be available throughout the year because of the storage which has been created. So how much average discharge is available throughout the year? You have to multiply the discharge which is available for a particular set of months. So let's say you have 10 meter cube for 4 months, so you have 10 into 4 over here, plus you add 6 meter cube for 2 months, so you add 6 into 2 here, and then you have 1.5 meter cube per second available for 6 months, so 1.5 into 6 here. So these are the number of months, 6 2 and 4. These are the number of months. So divide that by the total number of months in a year, you'll get the average discharge as 5.08 meter cube per second. So on average you have 5.08 meter cube per second available throughout the year now. So with this discharge, you are able to produce a power which is 1962, which was for 10 meter cube per second, into 5.08 divided by 10. That gives you 996.7 kilowatt. So throughout the year, 996.7 kilowatt will be available from your plant. You only require 400 kilowatts from it, so you will be able to supply the factory. No standby units will be necessary, and excess power which is available from the plant throughout the year will be 996.7 minus 400, which gives you 596.7 kilowatts. So 596.7 kilowatts will be available from the plant throughout the year, uh, after providing power to the factory, which is shown here. So it always benefits to create a reservoir and then store the water in that reservoir during rainy seasons, and then use that water during the dry spells to ensure that the water discharge rate does not fall below the critical level.